Welcome to the fourth video of our jet engine series. On the last episode, we calculated the thermodynamic properties at the inlet. And on this video, we'll start our modeling of the compressor. Let's dive in!
Trois, deux, un, top.
3, 2, 1, half. The Flight Test Engineering channel.
One of the most complex components of a gas turbine is the compressor. Its design needs to be robust enough to allow for operation from very small mass flow at engine start all the way up to maximum at takeoff, and at the same time operating as efficiently as possible during cruise. The compressor needs to deal not only with the mechanical nightmare of rotating parts at high speed, but also complex aerodynamics of the compressing gas that may stall the blades and block the passages along the way. But oh wait, you can use CFD to compute the flow and let the computer figure it out, right? Well, let's have a look at this awesome click from Onera, and thank you so much for sharing this video. This is a large eddy simulation model with meshes that have curvilinear grids along the walls and a Cartesian grid in the channel itself. We can see the complexity of the flow and how hard it is to create a high-fidelity model. This took only 58,000 hours worth of computing, and of course they had 656 cores, so it took about 4 days on a multi-million-dollar computer, not counting the hours to create the geometry, to the mesh, etc. And this is for a 3.5 stage compressor only. And let's see, the GE90 has 10 stages, so like I said, it's not a simple task. We will not be so ambitious here, and as stated in the previous videos, we'll be modeling a very simple turbine. But it's important to appreciate the complexity of the problem and understand our modeling has very big limitations. So we just need to be aware of this. If you want to follow along, you can access the Flight Test Engineering GitHub site, and then in there, there's going to be the gas turbine propulsion repo. And if you access that, there's going to be the Turbojet subdirectory, and in there, you will find the episodes 4 and 5 compressor notebook. If you check it out, it's going to have all of the equations there, and also all the code is going to be represented in these 2 episodes. And if you want to download, you just access this button here, and it will download directly to your desktop. We start where we left off on the previous video, with the air coming in from the inlet and arriving at the stagnation pressure P02 and stagnation temperature T02 at the face of the compressor. Now, no machine is perfect, and we'll need to figure out how we'll account for the losses. It's reasonable to assume that the flow will not exchange heat as it goes through the compressor, and that the losses will come all from the friction with the walls and the rotor. So we can then use the same assumptions we use for the inlet, meaning that we will lump all losses on a single value, the compressor efficiency eta C. Starting with the same efficiency definition then that we had before, which is the ratio between the ideal and the actual work, because we assume that we have an ideal gas and because we are compressing just a little per stage, we can assume that the specific heat contains is constant and does not change as we go through each small stage of the compressor. And then we can write the efficiency as this, T prime 03 minus T02 over T03 minus T02. And then we can pull in the pressure ratio for isentropic process, P02 over P01 equals T02 over T01 to the gamma minus 1 over gamma, and exchange this ratio here for the ratio of pressures, as we did here. And that leaves us with this expression for T03, which we'll use throughout the series. T03 equals T02, and so forth. Notice that up to here, we did not consider any variations in the operating conditions. We have the compressor running at 1 RPM and 1 mass flow, which will result in a particular pressure rise, the P03 over P02, and this is fine for one design point. like we mentioned in the previous video, but it is important to be aware that the limitation of such a single point model has. We can use a simple scenario here to understand the intuition. Suppose that you are holding a small working fan on your hand, and if you partially block the outflow, the fan will slow down because it will try harder to push the same amount of air through, but it can't. And at the same time, if you measure the pressure at the exit, it will have increased a little bit. So by changing the exit conditions, we change the pressure ratio and the mass flow. And on the same token, if you partially block the inlet, the fan will speed up trying to keep up the flow going. And the inlet and exit pressures will be lower than the unblocked case. And how do you think that the compressor flow properties change as the inlet and outlet conditions change? Normally, this is the type of graph that you'd see in the literature to illustrate this point. What we have here is mass flow along the x-axis and pressure ratio along the vertical axis. And these islands here that we see as thin white lines are the compressor efficiency. These thicker lines here are the RPM lines. So each one represents 1 RPM of the compressor. And this line here running along is the running line or the operating line. We'll go into this in a moment. So let's have a look at this in the 3D space. So this is called the compressor map. And as we said, the model we are building here is very simple and limited to the design point only. If we wanted to expand to other operating conditions, for example, partial throttle setting, we would need to move along the operating line and change mass flow and pressure ratio and efficiency all at the same time. So to expand the model, we'd have to have a compressor map like this one. The equations and equilibrium checks, stall, choke, flame stability in the combustor, needed for a model capable of reasonably accurate outputs at off-design points are much more complicated. But stay tuned because at a later video, we'll see one right here. The peak of the map is typically the design point. We want the machine to operate close to its maximum efficiency as much as possible. And the operating line is the line that matches whatever RPM the machine is running with the inlet conditions, read mass flow and pressure, resulting in a pressure rise with a certain efficiency. Notice how for a fixed RPM, the lines are almost vertical on the right hand, meaning that the pressure rise is a range for a fixed mass flow. Remember, mass flow is down here. As we pick a higher RPM, a line more to the right here, because the compressor blades are turning faster, the pressure ratio is higher and the rear stages have no problem accepting the mass flow, but this is not the case for the front stages. And at some point, one or more of the front stages will stall, effectively clamping the mass flow, we say blocking it. And what happens when the compressor runs at speed below the design point? Well, each stage will compress less, meaning that the temperature and the pressure rise will be lower, and consequently the density will be lower as well. This will lead in turn to the rear stages operating at a much closer to a blocked state. And if the local speed of sound is reached, then it will operate blocked, limiting the mass flow as well. This is basically the mechanism that limits the operation on the lower bound of this graph, and all the way to the vertical lines on the right. Let's have a quick look at the velocity vectors at the blade. What we have here is the blue arrow representing the flow velocity, the actual airflow, and the red arrow representing the rotational velocity of the blades of a compressor, for example. And here, the green arrow is the resultant airflow velocity that will impinge on the blade by composing both movements. And you can see that ideally it will impinge on the blade at some angle of attack that will render low drag, meaning higher efficiency. And let's have a quick look here at the changes that happen with this triangle of velocities as we change, for example, rotational speed. As we decrease speed and slow the compressor at a lower RPM, you can see that the red arrow reduces, and then this angle here between the green arrow and the chord line will decrease as well. So you can see that as you spin slower and slower and slower, your angle of attack will be lower at the blades. So on the opposite side, if we increase the rotational speed of our compressor, this vector here, the red arrow, is going to increase and will result in an increase in angle of attack of the flow coming into the blade. So this is what would happen. And of course, when you reach a high enough angle of attack, your blade stalls, and that will have a pretty bad effect on your compressor, as you might guess. Let's go back to our compressor map and identify where we have the stall and choking of the blades. And oh, by the way, if you're wondering what is the typical axial speed, that would be around 150 meters per second. Notice also that as temperature goes up, so does the local speed of sound, meaning that higher temperatures will give you more mass flow. The upper limit on the island here on the graph is due to stalling of the blades. This is where the blades will stall, as we saw, with lower rotational speeds and lower mass flow. You can see also that as you throttle the engine, the running line shows how the operating conditions will change. Notice how the operating conditions are limited on either side of the running line, and also how the efficiency falls rapidly to the right of the design point over here. If we take 1 RPM starting from the design point and we throttle back by reducing the fuel on the combustor, the mass flow is reduced rather quickly, and the compressor's pull takes more time to reduce its RPM due to inertia, and both of these effects tend to increase the AOA, especially at the initial stages. And eventually it will result in a stall at the compressor surge line, which is right there. As we keep the RPM and reduce the mass flow, you reach the surge line. The surge line runs on the tip of these RPM lines here. And since the front of the stages are stalled, the rear stages start to experience reverse airflow. And to overcome these problems, one of the most common solutions is to implement a bleed valve at a few of the stages. And this way, by reducing the mass flow in a controlled manner at these lower RPMs, you change the axial velocity, and we can change the AOA of the blades. Another way to tackle this problem is to use a variable geometry vane that will adjust the AOA according to the RPM. Again, because we're implementing a simple model, none of what we just discussed will be considered, for now at least. One last concept that we need to talk about is the different pressure ratios when we have a stack of stages. When designing the compressor, it is desirable to keep the temperature rise for each stage on the same ballpark, and this can range from as low as 10K all the way to 50K. And in order to achieve this, the front stages are more heavily loaded than the rear stages, meaning that the pressure rises are not the same and will be higher in the front. The rear stages also suffer from boundary layer thickening, since the stage blades are smaller and smaller, and the proportion of boundary layer affected and unaffected increases, and that forces the design of a smaller pressure rise on the rear stages. We'll also address this when we are coding the compressor in a short while. Okay, and now that we have some appreciation on the complexities of compressor design, we are ready for our next video where we will code our compressor in Python. I'll see you there!